Okay, Bismillah Rahman Rahim. So we are on to the second lecture of deep learning. Today we are going to be having a 1.5 hour class. In the last class, we laid the foundation for some, the foundation of deep learning based on artificial neural networks. Obviously, artificial neural networks, they form the stepping stone for deep learning algorithms. So we have to understand the artificial neural networks in extremely minute detail before we can start with convolution neural networks and other deep learning networks that are so famous. Okay. So just a recap of the last class. So we laid the foundation for the architecture of the neural network, the layers, the activation function, the perceptron, and the sigmoid neurons. We did some exercises as well. In fact, 2 exercises. So today we are going to start with the concept of the layers again. So as usual, you must be knowing right now that we are having 3 types of layers. The output layer, the input layer, and obviously 2 or more, or maybe you can say 1 or more hidden layers. So hidden layers are found right in the between, and the input layer is here, the output layer is here, obviously, and this defines the architecture as usual of a neural network. This is very easy to configure now in TensorFlow. You just have to add the layers, I think, which are provided by the Keras API. So Keras is now part of TensorFlow. So you don't need to worry about it, but I'm going to ask you to implement the backpropagation algorithm purely in Python, so that you can so that you will be able to understand the maths in a better way. So I will be giving that assignment on Friday, not today. Okay. Okay. So we saw that if the input are images, so then these each pixel becomes one particular input. So if I have 64 by 64 image size, so that means I will be having 4096 neurons in the input layer, and every input is going to have a value between 0 and 1, because in the grayscale 1 means black and 0 means white. Okay, so in that way you will be defining a whole picture. And also please remember very clearly that in the deep learning scenario, when you work on images, then typically you
Today have with us Abdul Sattar.
Ahmed Raza, please mute the mic. Thanks. Okay, so you must remember that when you are working with images, then you almost always do some sort of image processing on the algorithms before you can give the data to the input layer of a deep learning neural network, or a deep neural network, or deep convolutional neural network, whatever. Um, the image processing part is very, very important. For example, you can do image segmentation, you can do edge detection, you can apply techniques just like histogram of gradients, or there are several other techniques which you can apply. You can sharpen the image, you can denoise the image, you can saturate the image, you can segment the image before you give it to the input layer. So kindly remember this fact very clearly. Okay. So when we do the convolution neural network examples, so I'll be telling you, inshallah, a list of all those. I'll be telling you a list of some more famous image processing applications that are done on the images. Okay. And then we talked about this thing that we are feed forward. What is feed forward? Who will tell me what is feed forward?
सर इसका मतलब ये है कि कोई भी आउटपुट जो है वो वापस लूप बैक होके इनपुट में नहीं जाएगी.
Basically, to
I
some
don't
extent,
think
that is
so.
what it means. It basically means that when you give the input at the input layer, it is going to keep on going ahead until something comes out at the output layer. Okay, there is no coming back of the input like a loop. That does happen in a particular type of recurrent neural network, which is called bidirectional recurrent neural network. But in that case, the scenario is completely different. In that case, we need the input to come back because that is more of a temporal learning
सर आपकी
scenario.
आवाज अटक गई है, मतलब कोई आवाज नहीं आ रही.
Can everybody else hear me properly?
जी सर, मुझे आ रही है। ये इसके एंड में मसला होगा।
वो नेट का प्रॉब्लम, प्रॉब्ली नेट का प्रॉब्लम होगा। चलें, कोई नहीं, आई होप इट विल बी रिजॉल्व्ड सून।
सर आपकी आवाज एकदम टोटली गायब हो गई, मैं या किसी और को भी ऐसा महसूस हो रहा है.
यार हेलो, आपका मसला है। हेलो।
अच्छा चलें, अभी आई विल कीप ऑन टॉकिंग, इंशाल्लाह आई होप इट विल बी फाइन. So just remember this fact that feed forward primarily means that I am going from left to right all the way at full speed, and I don't care for going back. I will never go back. I will never loop back. Okay, that is basically what you mean by a feed forward neural network. Some Arif, okay, right. So we discussed this last time as well. This is definitely a deep learning neural network, although we have only, in this case, we have only one hidden layer. But I told you that we need to experiment with the number of neurons. So whenever you have a deep learning problem, you have to experiment with many different parameters before your solution can converge. That's what you have to learn, inshallah ta'ala, in this course. So in this case, we have 784 neurons because this data set is taken from the MNIST data set, which we will do today, inshallah. In this case, each image is of size 28 by 28, so that translates to 784 neurons in the input layer. And what we have to do is that we have to train the neural network. In this case, we will be training obviously a convolutional neural network because we are working with images. We have to train the neural network to basically detect whatever number we have. So if I input 5 at the input layer as a test data, then this whole vector will be 0 0 0 0 0 1 0 0 0 0. Okay, so that's what we wanted to happen. So I asked you last time why we are having 10 different output neurons and why not 4 binary neurons, because I have to output 10 different things like 0 1 2 3 4 5 6 7 8 9. So there are 10 different things. If I have 4 binary neurons, then I can model it like this. Like for example, 0 0 0 0 represents the number 0, and 0 0 0 1 represents the number 1, and 0 0 1 0 represents the number 2, and so on and so forth. In this way, I can have this. So I asked the question, why are we taking why are not we taking 4 binary neurons, and why are we taking 10 different neurons where each neuron will fire for one particular number? So what is the answer to that?
सर आपने बताया था accuracy issues होते हैं, that's the only major reason.
No, that's look, the accuracy issues can only be confirmed when we do the experiment. But what is the logical reason for that?
सर वो आपने कहा
Sir,
था कि चलो आप बोलो पहले।
जी,
go ahead.
सर आपने कहा था कि हमें फिर ना मॉडल को ये भी फिर इस तरह भी ट्रेन करना होगा कि ना आउटपुट बाइनरी में देना, तो उसकी अलग, यानी कि फिर मॉडल काफी कॉम्प्लिकेट हो जाएगा, आपने इस तरह कुछ कहा था।
नहीं, इसका मतलब ये है कि आप लोगों ने रिवीजन नहीं की लेक्चर की। जो कि अच्छी बात नहीं है. You need to revise the
प्रोग्रेसिव
lecture.
लर्निंग होती है इसलिए.
नहीं, देखिए, the answer is के if I associate a single neuron to each digit separately, so it allows the network to learn in a better way. And the reason is that I told you, which is coming in the next slide, the reason if I have to learn, if the network has to learn the number 5, right, it has to learn the number 5 over these weights and biases and over these weights and biases, okay, and obviously using these neurons of the hidden layer. So it has to learn the number 5. So I told you in the beginning that deep learning is incremental learning. So I will learn the low level features, and from that I will learn the high level features. So for example, if I have to learn the feature 5, then I will first learn something like this. Then I will probably learn something like this. Then the system will learn something this, and then this one, and then this one. Okay, and then it will learn that all these different parts together, they form the number 5. Okay, so this kind of incremental learning is more closely associated with a separate neuron, because if we mix the inputs with 4 binary neurons, then it does not give me that much flexibility to learn these patterns in a good way. That becomes, too strict, because I'm using all the 4 outputs for each number. So it might not be possible for me to basically logically visualize it. If I am learning a digit, if I'm learning to recognize a digit based on the parts of that digit, then it makes sense to make a separate output neuron for that particular digit only, so that the pathway for learning that is clearly defined. Otherwise, if we have 4 neurons at the output layer only, okay, and then I have to use these 4 neurons for each number. Each number will require these 4 neurons, and then it might not be easy for the system to learn these incremental shapes in a better way with 4 output neurons. This is a hypothesis which has been clearly validated by experiments. It might not be true in other cases, but in the case of MNIST and convolutional neural network, this is definitely true. So it is always better to have a separate neuron for each particular output, and then it will be easily manageable and also easily learnable. So you have to understand this incremental learning thing, and then you will be able to answer the question. Okay. So finally, do revise the lecture before coming to the next class. So this is the thing. Like for example, if I have to learn 0, so 0 can be learned incrementally in a feed forward way from here to here by learning these different shapes, and at the end we can say that 0 comes out here in this shape. Okay, so we are defining a clear path for the system to learn the value 0. That's what you need to understand. Okay, so now this is an exercise that you guys have to do right now. So now what's the difference? So I have 784 neurons here. I have I have a hidden layer which is consisting of 5 neurons. This is the old output layer which consists of 10 neurons, and this becomes the new output layer. So what I have done is in the old output layer, each neuron is basically representing outputting one number, okay, 0, 1, 2, and up all the way up to 9. I hope that this is clear. Now I am mapping this to the 4 neuron use case which we were discussing previously. So now every digit here gets mapped to this 4-digit number. So 0 can be 0, 0, 0, 0, 0, 0, 0, 1, 0, 0, 1, 0, 0, 0, 1, 1, 0, 1, 0, 0, 0, 1, 0, 1, 0, 1, 1, 0, 0, 1, 1, 1, and so on and so forth for the 9 numbers. Okay. So now the question is, find a set of weights and biases for the new output layer. See, what will that be?
Sir, can you repeat the question?
It is written here, find a set of weights and biases for the new output layer. So what will be the weight? Because the weights and biases mean the weights are all the weights which are coming on these lines. So these are the weights that we need to learn. And remember that the input layer does not have any bias. The bias is only associated with each neuron in the hidden layer and each neuron in the output layer. Please keep that in mind, okay? The input layer does not have any biased neurons. The bias is only associated with each neuron in the hidden layer and each neuron in the output layer. So now, as I have added another output layer, which is in fact, this is the output layer now. Now this becomes in fact, sort of a hidden layer. So now the question is, find a set of weights and biases for the new output layer. See, assume that the first three layers of neurons are such that the correct output in the third layer has activation at least 0.99 and incorrect outputs have activation less than 0.01. So yeah, I'll just stop the recording until we get the answer. Recording, yeah. Okay, so this is the MNIST database. Yeah, so I was talking about Leekan. Leekan is currently in Facebook. So this guy actually did the first successful application of convolution neural networks, which found its way into research and laid the foundation for other deep learning applications. I think this was not done on GPUs. Lee Ken is one of the pioneers of deep learning, along with Joshua Bengio and Jeffrey Hinton and a few other guys. Okay. So we have 60,000 training images and 10,000 training testing images. And I told you before that they are from 250 employees, out of which 125 are from the Census Bureau and the remaining are from the students, high school students. Okay. You can see that the digits have been size normalized and centered in a fixed size image. So that's the processing that they've already done. And these images are now available in Keras, so you can call them directly. You don't need to download these files, so you can call them directly. But the data set is primarily solved, and the primarily solved means you have achieved up to 99.99% accuracy on MNIST already. So you see, this is the history of the applications. So the error rate is 12% here, 8.4. This is way back in 1998. So you can see the things have started to improve. 1998. In 2007, it's 0.54. It's increasing even. So the error rate keeps on decreasing. 2009, 3.3, 1.68, 0.56. And currently 0.39 is I think, it even goes 0.35, 0.23. So, there are 0.23 error rate is basically, 99.93% accuracy or 99.3% accuracy. So even I think the performance is much better than this one. So it's almost 99.99% you can achieve on the MNIST data set. So yeah, so these are the different file formats. This is a different information. So like I told you, you can call it directly asset image file, IDX file format. If you like coding yourself, you can just try to download this through Python directly. So there are many blogs which will help you get started with MNIST database. So the point to understand is that why should we be interested in such a data set? Because it's good for people who want to try learning techniques and pattern recognition methods on real world data, while spending minimal efforts on data wrangling or pre-processing. Okay, it helps you build a sort of a test bed for your future convolution neural network tasks. So if you want to understand how convolution neural networks work and you want to do some very rough experimentation before you do some actual experimentation, then you can do that with the MNIST data set. because MNIST data set has been tried and tested by probably 100,000 of users across the world. And it's a very famous data set, and it's achieving very good accuracy, remarkable accuracy. So that's the thing that you need to remember about MNIST. Okay, I think yeah, so we'll do this later on. Just yeah, so now you have to concentrate now very thoroughly. Each training input is an image of a 784 dimensional vector, which you already know. And this is also, you know, that it represents a grayscale value. So yx is a 10-dimensional vector, which you have seen in the previous slides. So if I have to output 6 from the deep learning system, then it is going to be output like this. Penta 0, 1, and quattro 0, Cach 0, okay. So it's going to be output like this. So 0, 1, 2, 3, 4, 5. Okay, what's this? 0, 1, 2, 3, 4, 5, 6. So this should be 1. I'm sorry, this should be 1. I did this wrong. This is the number 5, in fact. Transpose means from row to column. Convert a vector from row to column, so you do the transpose. So typically we write it like this. Yeah, so our job, now we come to this gradient descent algorithm slowly. Our job is basically to minimize this error. So you must be able to recognize this this equation. This is the cost function. This is the actual value, the actual digit, and this is the activation of the output neuron. And obviously we have to ensure that the values match exactly. So the digit which is output by the system in a feed forward way is actually the digit which we want. And this double signs mean that I'm taking the magnitude, and square obviously the square of the magnitude. So basically this is also a vector, this is also a vector. So I am subtracting the corresponding terms from the vector and then taking their squared and summing them up. And n is the size of the training data. So keep that in mind. So if you have 60,000 vectors, then n is going to be 60,000. Okay. And obviously the cost is, I told you, I think in the last class that the problem of deep learning is to learn the values of weights and biases, which is going to help me minimize the cost. What are the values of weights and biases that are going to help me minimize the cost? So for that, first of all, I have to define a cost function. The cost function is defined, as you can see right now. This is a quadratic cost function, but we can define many other cost functions as well. Quadratic function we are defining right now because of the fact that it is easier to understand, and it is easier to understand and work with in the case of neural networks. But we can have other functions as well. So please remember that yx is a vector, a is a vector. I am subtracting the relevant terms for these two vectors, and then summing up the difference, squaring the difference, and then summing up all the square differences, and then dividing them by 1/2 to the 2 multiplied by the number of training images. So I can, yx is yx, which is output by the out system, but I can express a in terms of obviously w and v, because a is coming out from the system. So I can express a in terms of w and v. So the output a depends on w, b, and x, as simple as that. Like we were looking at in this case, that's what I was telling you there, that the output of this neuron is depending on the weight value here and the bias value here, and the x value which comes out from here, which is the activation. So activation of the previous layer becomes the input to the next layer. Activation of the previous layer becomes the input to the next layer. So the activation of the previous layer becomes the x for the next layer. X gets multiplied by the weight plus the bias, that gets input into the sigmoid activation function, and then it will fire or not depending on how much input is there. So please keep this fact in mind at least. Okay. ठीक है, अभी तक clear है? Is this thing clear?
सर ए क्या चीज है?
Sorry.
सर ए क्या चीज है?
ये क्या चीज है? Who is going to answer this?
So it's the activation threshold.
देखें, every neuron in the hidden layer and every neuron in the output layer is going to output something. That output is called the activation value that we represent primarily by A. सही है? This is going to output an A value. इसको हमें subscript देना पड़ेगा. We are going to put it in subscript, but we are going to put it in subscript only when we do the back propagation neural net algorithm on Friday. Otherwise, it is going to get too confusing right now. Always remember that every line that you see here has a particular weight value that you have to learn. The input to this line is the activation coming from the previous layer. And we are presenting the activation by the letter A. This A is primarily X that we input here. So every layer mein we are taking X as A. This A is get multiplied by the weight of this particular synapse plus the bias. So the bias is a value which is associated with each neuron in the hidden and the output layer, not the input layer. And every neuron has a separate bias value that you have to learn. That is why deep learning is complicated. It can generate hundreds to thousands of different parameters of weights and biases that you will need to learn before the deep learning network can converge. So it's not easy. It's not easy. So every neuron has a separate bias. Every line has a separate weight. And for a particular synapse, the input to that synapse is the activation from the previous layer. The input to this neuron is actually Wx plus B, where X is the activation of this, W is the weight of this, bias is this, and then we are going to put that into the activation function, which is going to fire or not depending on the total input. Okay. So what happens is I know that if I have input a number here which is 0, मैंने image input किया है जो कि 0 है, I am expecting the system to output 0, 0, 0, 0. Because that corresponds to a 0 in my case. Okay. So this thing is actually Yx. But I already know it should be like this. But what comes out of here is not Yx, that is called A. That's the vector A. So maybe Yx is 0, 0, 0, 0 because आपने input पे 0 दिया है, तो obviously output पे 0 है. But let's assume that the output comes out to be 1, 0, 1, 0. That means the system has not learned. The system has to learn the weights and biases so that the output becomes 0, 0, 0, 0. Okay. So this becomes my vector A. And this becomes my vector Yx. So I have to do Yx minus A whole square divided by 2n by summing. So 1 minus 0 whole squared plus 0 minus 0 whole squared plus 1 minus 0 whole squared plus 0 minus 0 whole squared divided by, I don't know, 1 over divided by 2 into 60,000, that is 1,20,000. Okay, so that becomes my cost that I have to minimize.
सर
जी
सर तो मतलब Yx वो आउटपुट है जो यानी कि असल में होना चाहिए ना उसको, और A वो आउटपुट है जो आपका मॉडल आउटपुट कर रहा है, जो कि गलत भी हो सकता है। ये आप कहना चाह रहे हैं?
Yes, yes, yes. And you keep this in mind that the output A is definitely represented in terms of weights and biases and X. ये तो clear है ना? This point should be clear in the minds of all the students. The activation A is definitely depending on the weight and the input and the bias. ये तो सही है ना? Because A equals to sigmoid of sigmoid क्योंकि if I am assuming the sigmoid neuron, Wx plus B. ठीक है? Is this thing clear?
जी सर।
So this is the same case in the whole deep learning neural network. Okay. Activation is depending on the weights and biases and the input value of that layer. So now what does this mean? इसका मतलब क्या हुआ कि activation में? इसका मतलब ये हुआ भाई कि I can represent the cost based on W and B because A can be represented in terms of W and B. अब आप मुझसे now my question is कि why do I need to represent the cost in terms of W and B? Why?
सर क्योंकि ये ट्यूनेबल पैरामीटर्स है
Huh?
So that we can minimize the cost and we can see the updated values of weights and biases.
Yes, the cost function will have a certain shape. That shape is going to be defined by the vector of weights and the vector of biases. My job is to minimize the cost function. Yani find out the minimum point on the shape of the cost function. Cost function की जो shape है, उस पे मुझे minimal point की तरफ जाना है. I want to find out the values of weights and biases, which are going to give me the minimal cost value. So let's see what that means. Acha, before I go to the details, this is a quadratic cost function, which is also called the mean squared error, and it is always going to be non-negative. Why?
सर स्क्वेयरिंग की वजह से
हाँ, square की वजह से the cost is always going to be non-negative. So our job is to minimize the cost. ठीक है? अब आपको ये सवाल मुझसे पूछना चाहिए था कि सर, why we are doing the cost in this way? ठीक है? Why can't we associate the cost with the number of images which are correctly classified? ठीक है? आप कहेंगे जी, do you understand what I'm saying? कि why you are calculating the cost in such a complicated way? You can simply say कि यार ये आपका, this is your neural network. I gave it 10,000 test images. It classified 5,000 properly, 5,000 incorrect. So my accuracy is 50%. That's it. Number of images correctly classified is what I want. That's it. Why do I need to have such a complicated cost function? Can you answer that?
सर इस स्लाइड के अंदर आपने स्टेट किया हुआ ग्रेडियंट डिसेंट का, तो ग्रेडियंट डिसेंट के अंदर जो है हम जब कैलकुलेट कर रहे होंगे तो उसके अंदर फिर हम ये वाला फंक्शन यूज कर सकते हैं. वो हम अगर इमेजेस की बेस के ऊपर करने की कोशिश करें तो पॉसिबल नहीं है उसके अंदर.
हाँ, if I am using this
हमारा
as the,
ट्रेनिंग डेटा भी कम होता जाएगा क्योंकि हमारा एक्यूरेसी कम होती जाएगी इस हिसाब से. क्योंकि हमारे अगर 50% एक्यूरेसी आई है तो हमारा इनपुट डेटा जो है कम हो जाएगा.
नहीं, इसका ये जवाब नहीं है. इसका ये जवाब नहीं है. देखें, अभी सवाल ये पूछा जा रहा है कि why you are using a quadratic cost function while I can use a very simple performance measure, which is the number of images which are correctly classified by the network. The answer is that I have to learn the values of weights and biases in order to minimize the cost. If I take this as the cost function, number of images correctly classified, I will not be able to represent the weights and biases in a smooth function. In a smooth function, which I can minimize using gradient descent. So let's say कि cost is like this in terms of weights and biases. Weights तो भाई देखें हजारों हो सकते हैं, biases भी हजारों हो सकते हैं. Right now I am assuming I just have one weight and one bias. Let's assume only one weight and one bias, and this is the cost function. My job is to find out the value of weight and bias that is going to give me the minimal cost. Understand? If I take this as the cost function, this one, the number of class, it is not possible for me to represent the cost as a smooth function which can be minimized. I can't do that because this is just a discrete number of wages correctly classified. I don't have a smooth function which I can minimize using this performance measure. But if I take a quadratic cost function, I can minimize that using the gradient descent algorithm by basically taking partial derivatives. You know, if I take the derivative, then that means what is the rate of change at that point? Okay, so I want the rate of change of cost to go towards the minimal point. So I can't work with rate of changes. So the point is कि इसको इस तरह सोचें कि if I start here, let's say I'm right now at this point, my cost is very high. I want to reach this point. So how am I going to go from here to here? What is going to convince me to come down? What is going to convince the cost function to come down? So this is actually learning W and B. So what is going to convince me? What is to do such a sort of stuff? I need to have a very robust mathematical equation as a cost function in which I can apply the gradient descent algorithm, which is going to reach this minimum point. If I take this as the performance measure, it is definitely not possible for me to represent the cost function as a smooth curve in which I can reach the minimum point. So there is no way I will be able to minimize the cost function in terms of weights and biases if I use this as the performance measure. Is this thing clear?
Yes, sir.
देखिए यहाँ क्या लिखा हुआ है कि making a small change to the weights and biases is not going to make any change to the number of correctly classified instances. That means ke, I want, this is what I told you in the last class, ke, I change the weights and biases, that should affect the output of the neuron. That should affect the output in the output layer. अगर आपको याद हो last class में मैंने ये बात की थी. Changing the weights and biases should change the output. That makes it controllable, right? I want to learn the values of weights and biases which will make the output or the cost as less as possible. So I want, if I change the weights and biases, the cost should be affected. But if I take this as the performance measure, then it is not possible to affect the cost. Lihaza, this performance measure is not going to help me find the optimal values of weights and biases through the partial derivatives. Okay, that is not going to happen. Therefore, I cannot use this because that makes it difficult to figure out how to change the weights and biases to improve the performance. I can't do that. I can't do any differentiation of a function which is not quadratic or cubic or whatever. And you should also keep in mind that I can use functions which are besides, it is possible to use functions which are not quadratic functions as the cost function I told you before. But right now we're going to be sticking with this example because it's easier to understand. ठीक है अभी तक clear है? Is this thing clear?
Yes, sir.
Okay, so now let's say that this is what we are looking for, right? So this is our cost function. Let's assume we just have two variables. So यहाँ पर हमने लिखा हुआ है V1 and V2, but let's assume that this one is the bias and this one is weight. I just have one weight and one bias. So just to give you an example of this function, this is the quadratic function which can be represented like this. So what I mean you to say is that I want to find out the point which is right here. इस point पे weight or bias की value क्या है? That's what I want to find out because that is what minimizes the cost. How am I going to find out? I have to take the derivatives because the derivative in this case is going to tell me the rate of change. So if I am at this point and I take the partial derivative of C with respect to V2 in this direction and with respect to V1 in this direction. So I take the partial derivative and I move this point थोड़ा सा उस direction में, थोड़ा सा इस direction में. I move this point. Now when I move V1 and V2 or when I move bias and weight, then that is going to move the cost function as well because the weights and biases are affecting the cost function based on the quadratic equation. So then that means I have the concept of a delta C, change of the cost function, change of cost, which is depending basically on delta V1 and delta V2. सही है, clear हो रही बात? Yeah, you need to understand this concept very clearly. Okay, I can only reach the bottom of the curve by taking the partial derivative of the cost function over a large period of time. And I am never initially at this point, because initially the cost is going to be high, the network has done nothing. So initially I'm going to be at some point here. At each point, I'm going to take the partial derivative of the cost with respect to each parameter. If I have 1000 weights and I have 1000 biases, then I am going to take 1000 partial derivatives for the weights and 1000 partial derivatives for the biases. There is a way to minimize that as well. We will see that. But typically, that's the ideal case that I'm telling you. So when I have these partial derivatives, then that means that I am basically moving the ball. I am moving a ball. Okay. So when I take the partial derivative with respect to each dimension, then I'm moving the ball in each direction somewhat slowly. मैं थोड़ा सा बॉल को मूव कर रहा हूँ. जब मैं सारे डायमेंशंस पे थोड़ी थोड़ी मूवमेंट करता हूँ, then the cost also moves. ठीक है. So the cost, delta cost, is always depending on the delta of all its dimensions. So in our case, the cost of the quadratic function is always dependent on the cost of on the rate of change of all the weights and the rate of change of all the biases. Okay, so we can use the concept of derivatives to find out C minimum kahan par hai. Because when we set the derivative equals to 0, then that means that you are at the minimum point. So we can find that out. So it is difficult when we have 100 to thousands of variables. So this is just an example for explaining to you, but typically we have hundreds to thousands of dimensions. Okay. If I take this as an example of ball rolling down the valley, it will eventually trickle to the bottom. सही है. If I take this, ये जो मैंने आपको बताया है process, if I continue this process, so I have to do some innovative stuff as well, because I have to ensure that the ball goes down. ऐसा ना हो कि V1 और V2 change करने से ball वापस ऊपर जाना शुरू हो जाए. That is also possible, but I have to design the partial derivatives in such a way that the ball always goes down until it reaches there. There is no way that the ball can go up. It will always trickle down to the bottom. Okay, so that is the trick that we have to play now in the gradient descent algorithm. So that is done using partial derivatives. Always remember that the cost is derivated with respect to all the weights and with respect to all the biases, because we have no other option. We have to learn the values of all the weights and all the biases. Therefore, I have to take the partial derivative of the cost with respect to all the weights and with respect to all the biases, and use those partial derivatives to find out the values of all the weights and all the biases. Okay, that's what we have to do. So we will formalize that on inshallah Friday. So typically now, so this is the case. So this is, you can take this as the ball. Okay, and the ball has to roll down to this point P, which is what we typically want. So now let's define some maths here. So this is the in fact cost function which we are defining. Okay. Now let's, अब आप थोड़ा सा इसको थोड़ा सा समझने की कोशिश करें. Move the ball a small amount delta V1 in the V1 direction, which is this one. This direction. No matter, let's say the ball is here, because when we start the process, the ball is right at the top because the cost is very high. The system has not learned. I said, okay, cost is very high, so let's try to reduce the cost. So move the ball a small amount of delta V1 in the V1 direction. So I said, okay, यार थोड़ा सा यहाँ move करो. ठीक है जी, मैं move कर गया. And a small amount in the V2 direction as well, because I have two dimensions. So I said थोड़ा सा इधर move करो, अब थोड़ा सा इधर move करो. ठीक है जी, मैं यहाँ move कर गया. ठीक है. So the new position is this one, right, on the curve. It has to be on the curve, obviously, because we can't go. The curve is defined to V1 and V2, so it will always be, the new position will be always on the curve. So now you see that this new position is a bit lower from this. So I'm going towards this. So how did that happen? So first let's make a representation. Delta C is this plus this. So I derivate I derivate cost with respect to V1 multiplied by the rate of change of V1 plus the, because I'm adding it up, right? So I first move in V1 direction and then I move in V2 direction. So when I move in the V1 direction, so there is a change, and I multiply that by the derivative value of the cost with respect to V1. And similarly, I do the same for the case of V2. So delta V1 and delta V2 should be chosen so that delta C is negative. That's the game that we have to play here. How we are going to ensure this one? That, like I told you in the last slide as well, okay, I can change delta V1 and delta V2 so that first it comes here, then it rolls back here to the top, then it rolls back here to the top, then it rolls to the top. It is possible for me not to go down, but I have to ensure that the cost changes in such a way that it always goes down. Then how can we do that? We can do that by controlling delta V1 and controlling delta V2, because that is in our control, and that control is somewhat influenced by the partial derivatives. So do all of you understand this equation?
Sir, is this similar to the learning rate?
Abhi, we're not talking about any learning rate. We are talking about changing the values of the parameters. Let's assume V1 is the weight and V2 is the bias. So what is this equation telling you? It is telling you the change in cost is actually the change in weight, okay? The change in weight plus the change in bias, which is true because the cost is being defined by the rate of change of weight and the rate of change of bias, which is true in our case, okay? So in this case, to simplify, we have taken V1 and V2. Actually, we're going to have W and B for each individual weight and bias. So is this equation clear?
Yes, sir.
Why we are multiplying the derivative by the rate of change? Why we are multiplying the derivative by the change? Can anyone tell me that? What is dC by dV1? How will you define that?
So the rate of change of the cost with respect to V1.
Rate of change of cost with respect to V1. That is okay. किस rate से change हो रहा है? Why do we multiply it by that delta V1?
डेल्टा V1 वो चेंज है जो हमने इंट्रोड्यूस किए चेक करने के लिए कि हमारे पास इस डायरेक्शन के अंदर कॉस्ट फंक्शन पे क्या इम्पैक्ट होगा. तो न्यू कॉस्ट फंक्शन फिर हमारी जो हम जितनी हमने चेंज की उसके ऊपर डिपेंड करेगा.
हाँ, the partial derivative is telling you the rate of change. So whenever the logical reason is that if I am changing V1, it has to change with respect to its rate of change, right? जो उसका rate of change बन रहा है उस हिसाब से change होगा ना वो. That is why we are multiplying these two terms. Okay, we want to change V1, we have to change V1 because the ball has to go down. If I change the parameters, then only the cost is going to go down. Okay, so I have to change V1 and I have to change V2, but that change is defined by their rate of change, which is given by the partial derivatives. कि ठीक है तुम change तो हो जाओ लेकिन तुम्हारा rate of change क्या है उसके हिसाब से change हो. That is why we are multiplying these two terms. ठीक है भाई देखें, please remember these concepts. That's what's going to be asked in your hourlies. You need to understand the concept of these formula. So I can represent this notation more clearly as this one. Let me take delta V as the vector of changes, delta V1, delta V2. So I just put this as a vector. And I can also put this partial derivative in a separate vector. So I'm taking that as the partial derivative के लिए I have taken the inverted triangle. Please note, the inverted triangle represents the vector of partial derivatives, while the right triangle, the not inverted triangle, represents the rate of change. Okay, so inverted triangle represents the vector. Oh no, sorry. Delta C represents the, not the rate of change, but delta C represents the change in cost. Okay, the actual change in cost. Like initially cost was, let's say, 35.9, and after you did this gradient descent, the cost came down to 32.9. So the change in cost is 32.9 minus 35.9, whatever. So that is delta C. So that is represented by the triangle, and the inverted triangle is representing the vector of partial derivatives. So we have only, ये हमने दो वेक्टर्स सिर्फ इसलिए लिए ताकि नोटेशन आसान हो जाए. So basically I'm representing this as this. Delta C equals to inverted C dot product with delta V, where delta V is V1 and V2, and obviously inverted C are these two partial. Okay, it's just to facilitate the multiplication of vectors. They are the same thing. Is this thing clear?
जी सर.
Yes, sir.
Okay, so so that's what we did. Delta C equals to inverted C dot delta V. So you can see what happens, what this is doing now. अब आप इसको थोड़ा ज़्यादा इंशाल्लाह समझ में आएगी. The partial derivatives are allowing me to relate my parameters with the cost. That's what they are allowing me to do. So अगर मैं आपसे सवाल पूछूं कि why in the world do we need to take partial derivatives in the gradient descent algorithm? So what's going to be answer? Your answer is, through the partial derivatives, we are able to control the change of cost with respect to the change of parameter values. Understand? We are able to control the change of cost, which is what we were, जो हम पहले डिस्कस कर रहे थे कि मैं चाहता हूं कि अगर मैं वेट और बायसेस को चेंज करूं तो कॉस्ट भी चेंज हो. That can only happen through a quadratic function, not through the other performance measure. So this is the catch here. Okay, that happens through partial derivatives. When I take the partial derivative, they allow me to associate my parameters or the change in my parameters with the change of cost. That they provide this link between change of parameters and the change of cost. So now I am in a position to basically minimize my cost. अब trick क्या हम खेलते हैं?
सर यहाँ पे आपको इंटरप्ट करूंगा, कर दूं या ना? कर चुका हूं. एक सा सवाल है मेरे को बिफोर वी मूव ऑन.
क्या सवाल है?
सर मैं ये पूछ रहा हूँ कि आपने बेसिकली ये डिस्क्राइब किया पूरा कि भाई द चेंज इन सी जो अपने इक्वेशन जो बेसिकली सबसे टॉप पे दिख रही है, डिस्क्राइब किया. सो इज इट करेक्ट टू से basically what we are trying to find is the lowest point, okay, on that plane, और उसके लिए जो ना we want to converge, we are trying to find the delta C जो उसे कम से कम नीचे से नीचे लेकर जा रहा है. पार्शियल डेरिवेटिव का जो मकसद है, जो मुझे एक चीज समझ आई है कि भाई इट्स फर्स्ट ऑफ ऑल चेंज विद रिस्पेक्ट टू अ पर्टिकुलर वेरिएबल, तो मतलब चेंज फ्रॉम फॉर द डिपेंडेंट वेरिएबल विद रिस्पेक्ट टू वन वेरिएबल रादर देन बोथ द वेरिएबल्स. तो जो पार्शियल डेरिवेटिव वाली लॉजिक तो है, आपको चेंज इन सी चाहिए तो ऑब्वियसली यू हैव टू डू इट इन पार्शियल डेरिवेटिव्स में इंडिपेंडेंट वेरिएबल्स दो हैं इंस्टेड ऑफ वन. ठीक है, एक चीज. फिर आप उसे मल्टीप्लाई इसलिए कर रहे हैं अपने डेल्टा v1 डेल्टा v2 से कि क्योंकि चेंजेस इन टर्म्स ऑफ v1 v2 होनी है, तो फिर आप जब उसकी रेट ऑफ चेंज को इनटू द चेंज मल्टीप्लाई करके सम अप कर रहे हैं, दैट्स वेल इक्विवेलेंट टू द चेंज इन द डिपेंडेंट वेरिएबल. ठीक है, ऑलमोस्ट change in dependent variable.
Yeah.
Okay. That makes it lower and lower.
हाँ बिल्कुल, because you know आपने सही कहा है कि we have to the change in cost, because we want the delta C to be always negative. Okay, we want the next cost to be less than the current cost. That is the only way the ball will go down. So for that we play this trick, which I will discuss right now. But जहाँ तक इस equation का ताल्लुक है, so you are right in the sense के main चीज जो मैंने आपको बता दी है कि taking the partial derivatives allows you to control the change of cost with respect to the change of the parametric values of the neural network. The other point is that if I am changing the values of the hyperparameters, obviously they have to change with respect to the rate of change. भाई मैं किसी को कहता हूँ कि भागना शुरू कर दो, ठीक है, तो he says okay I'll start running, तो लेकिन how fast can he or she run? What is the rate of her or his running? He can only run with respect to that rate. So that is why we have to multiply these terms. Okay. So now the trick is that how do we ensure that delta C always has a negative value at every learning step? If the cost was time t0 pe cost थी 35, time t equals to 1 pe I want the cost to be 33, for example. Then I want the cost to be 31, for example. And similarly, I want the cost at the end to be 0. So at every next timestamp, it is the less than the current timestamp. So the delta C has to be negative always, always, always. Because 33 minus 35 is negative, 31 minus 33 is negative, and so on and so forth. So how do we ensure that? We ensure that by taking delta V equals to a parameter minus of eta and inverted C, the partial derivative vector. So I basically model delta V as this one. If I assume this, it's a eta is a small positive parameter called the learning rate. Okay, so I basically introduce this deliberately myself. So if I plug in these values here, so this is the equation, and then I put this equation in here. So the delta C becomes minus of learning rate and partial derivative square. Okay, partial derivative square. So now you can see that delta C is being represented in terms of only partial derivatives and the learning rate. So this square will always be positive, will always be positive. So when it is always positive, it is 100% sure that delta C at every learning step will always be negative, because we are having a negative sign here, and n itself is positive and cannot be negative. So this whole term will be negative. So that will ensure that the ball is always going to go down. Okay. So this is a trick that we play. We just introduce a negative learning rate multiplied by the partial derivative vector again. So that is partial derivative vector squared multiplied by the negative of the learning rate, and that is going to give me a surety 100% that the delta C is always going to be less than the previous time step. So it's guaranteed that delta C will always decrease in the next timestamp or the next learning time. So by modifying the value of delta V, we can ensure that the ball definitely rolls down the cost slope till the minimum point. So this is what we do. So when we update V, so we update V like this, give V equals to the, please wait, just 1 second. Any parameter like W, let's say I have W1. So W1 equals to current value of W1, because देखें हमने weights को biases को update करना है, but we have to update them in such a way that the cost decreases. And the cost is going to decrease when we introduce this term of negative learning rate. So if I have to update the weight vector at each learning step, so let's say I'm talking just about one weight, W1. So the equation is going to be W equals to W1, which is the current value, and this is the new value of W1, minus the learning rate and delta C. And delta C, you know what that means. That is the that is the vector of partial derivatives. So in this case, it will be probably dC divided by dW1, because here we are only concerned with W1. We are not concerned with all the partial derivatives. I'm only concerned with the partial derivative of dC with respect to W1. So if I have to update W1, so W1 equals to the current value of W1 minus the learning rate multiplied by the partial derivative, and that is going to give me the new value of the weight with the surety that the cost is definitely going to go down. Is it clear now? Is this thing clear?
सर ये मुझे ये समझ नहीं आया, डेल्टा वी इक्वल्स टू माइनस एन और वो उल्टा ट्रायंगल सी कैसे?
भाई आप
ये दूसरे
बात
पॉइंट में जो है
आप सुने तो सही, मैं इतनी ध्यान से समझा रहा हूँ, मैं ये तो आपसे कह रहा हूँ कि वी मेक दिस रिप्लेसमेंट आवर सेल्व्स, ठीक है, बिकॉज
अच्छा
वी डेफिनेटली हैव टू एंश्योर कि डेल्टा सी is negative at each learning step, because that means the ball is going down. यहाँ पे कॉस्ट हाई है, यहाँ पे कॉस्ट कम है, सो डेल्टा सी जो है वो क्या होगा, नेगेटिव होगा। सभी ये तो बात समझ में आ रही है ना?
जी सर।
हाँ, तो डेल्टा सी को नेगेटिव करने के लिए आई डू दिस ट्रिक ऑफ द लर्निंग रेट, कि आई से कि द चेंज इन द पैरामीटर, क्योंकि देखें हमारा मकसद क्या है कि I want to change the parameter values so that the cost goes down. So I have to define a equation for changing the value of each hyperparameter, each weight and each bias. I have to define an equation for that. Now, how do I define the equation so that the cost always goes down? For that, I play the trick of this learning rate. So I say that the rate of change of any hyperparameter is equal to, at a generic level, the minus of eta multiplied by the partial derivative for that particular hyperparameter. And that is definitely going to ensure your cost is going to go down at each learning step. That is all you need to remember. Okay? How it ensures at a generic level, ये मैंने आपको plug in करके दिखा दिया. This was the equation. When I plugged in this one in this equation, so this delta C became this. So when delta C is minus the learning rate is always positive. So this becomes a negative value. Inverted C squared is always going to be positive because it's a square value. So then that means that delta C is always going to be negative, and that solves our problem. So अब हमने सिर्फ करना ये है कि this equation, basically this equation is doing what? It is telling you a trick for updating each and every hyperparameter that is going to lower the cost. That is all you need to remember. अगर ये बात समझ में नहीं आई तो प्लीज आप मेरी वीडियो दोबारा सुनिएगा, ठीक है? ठीक है जी, क्लियर है?
जी सर।
Okay, so it's 10:30 as well.
Yes, sir.
So this is the example of the ball that we want to take down. Just 5 more minutes and then I will finish. So you understand this now. I just repeated from the previous slide. Understand this now as well. And now we have the concept that I can update each weight and I can update each bias in such a way so that the cost goes down. Now I have the trick for that. Okay. So what I do is that at each learning step, I compute the partial derivative factor and move in the opposite direction. How will I move in the opposite direction? By doing minus the learning rate. So W1 new equals to W1 current minus eta multiplied by dc over dw1. ये क्वेश्चन तो समझ में आ गई है ना? This is going to ensure that the cost is going to go down. B1 new equals to B1 old, or sorry, current minus eta multiplied by dc divided by d divided by
B1.
B1. देखें जो हाइपर पैरामीटर अपडेट हो रहा है, वी आर ओनली कंसर्न्ड विद द पार्शियल डेरिवेटिव ऑफ दैट. Why do I other will always be zero for me? When I am derivating with respect to B1, all the other partial derivatives, I don't care about them because they don't contain B1. Similarly, I will define this equation for all the possible weights and biases, and I will use this equation to find out the values of weights and biases which are going to minimize the cost. Khatam, finish. So at each learning step, I have to take the partial derivative. तभी यहाँ पे ये चीज लिखी हुई है. सही है. अच्छा, अब इसमें एक ट्रिक ये है कि eta needs to be small enough, otherwise delta C will be greater than 0. Agar if eta is very large, okay, if eta is very large, then what will happen? यहाँ से बताएं.
But it will move beyond the minimum point.
हाँ बिल्कुल. Inverted C square. So if eta is very large, then what will happen? Then delta C might become very less, right? क्यों जी? अच्छा हाँ, अगर ईटा बहुत छोटा है, जैसे मैं कहता हूँ 0.00001, then obviously it is going to take a lot of time for these costs to go down because you are updating it in a very small magnitude. ये बात तो समझ में आ रही है ना? Are you getting this point, everybody?
सर इसको रिपीट ही करते हो तो बेहतर है सर.
देखें
सर वो डायरेक्ट जंप मार के बिल्कुल मिनिमम पॉइंट पे आ जाएगा.
हाँ देखें, अगर मैं कहता हूँ कि ये इक्वेशन आपके सामने, मैं कहता हूँ ईटा की वैल्यू है 0.0001, ठीक है, ये इक्वेशन आपके सामने है. व्हाट हैपेंस? चेंज ऑफ कॉस्ट इक्वल्स माइनस तो हो रहा है चेंज ऑफ कॉस्ट, लेकिन चूंकि मैंने इसको 0.00001 से मल्टीप्लाई कर दिया है, तो क्या होगा? चेंज ऑफ कॉस्ट बहुत कम हो जाएगा ना, तो इट इज गोइंग टू गो डाउन वेरी स्लोली. डू यू अंडरस्टैंड? भाई अगर n की वैल्यू 0.00001 है, तो डेल्टा सी पे क्या फर्क पड़ेगा? डेल्टा सी भी कम होगा, सही है ना? हेलो हेलो,
जी सर.
भाई कहाँ खो गए सारे? इट्स अ सिंपल इक्वेशन यार, कम ऑन. दिस इज डेल्टा सी इक्वल्स टू दिस. if n is very small, then what happens to delta c? delta c नेगेटिव तो रहेगा, लेकिन बहुत आहिस्ता से अपडेट होगा.
Yes.
So it is going to come down very slowly. We don't want that. On the other hand, if this is very large, then what happens? Then tell me. If I say eta,
skip मार सकता है वो एक्चुअल जो कहते हैं मिनिमम पॉइंट है, उसको स्किप मार के आगे जा सकता है. और
हाँ,
इस तरह
skip
मतलब
मार
बहुत
के
ज्यादा
आगे जा
random skip.
सकता है. स्किप मार के आगे जा सकता है बिकॉज इट्स, अगर मैं इसको 0.99 रखूं, सो दिस कुड, हाँ वो इतना चेंज हो जाएगा कि इट विल मिस द मिनिमम पॉइंट. अंडरस्टैंड? इट विल चेंज सो मच कि फॉर एग्जांपल इट्स गोइंग टू कम डाउन हियर एंड व्हेन इट इज क्लोज टू मिनिमम, आपने n की वैल्यू बढ़ा दी, देन इट अगेन गोज बैक अप. अंडरस्टैंड? समझ में आ रही है? सो आई हैव टू, इसीलिए लर्निंग रेट इज अ कंट्रोलेबल पैरामीटर which would typically, initially learning rate is high because the system has not learned. Slowly the learning rate goes down. ठीक है? If the learning rate is very small, then the cost is going to go down very slowly. If the learning rate is high, then you might miss out on the minimum point because delta C might increase a lot if the learning rate is high. ठीक है? It could even go greater than 0. Then I can miss the minimum point. So I have to maintain a balanced learning rate so that I definitely reach the minimum point. So I think we'll finish it here. So I will advise all of you to please go through this lecture before the next class so that we can have an active conversation. Otherwise, I will have to repeat many things. Please listen to the lecture before you, always listen to the previous lecture before you come in the next class. ठीक है?
सर
ठीक है सर.
अच्छा,
सर मैं कह रहा था कि अगर ये ज्यादा छोटा हो, सर ये ईटा अगर ज्यादा छोटा होता है तो ये लोकल मिनिमम पे भी फंस जाता है ना. ग्लोबल मिनिमम
जी
अचीव
जी
करने में
बिल्कुल,
इशू होती है।
that is also possible. If it is very small, then it can also get stuck in a local maxima, क्योंकि the cost will be changing very slowly. ठीक है, the cost will be changing very slowly, and if the cost is changing very slowly, then it could get stuck in a local minima and consider कि यही मेरा minimum, बस यही इसी को हम minimum करेंगे. So therefore, we have to play with these hyperparameters in such a way that this does not happen. Achha, I wanted to show you some hands-on, basically. I will upload this. ये मैं आपको Friday को दूंगा, क्योंकि अभी ये चीजें थोड़ी सी जब तक हम back propagation पूरी नहीं पढ़ लेते ना. So you can import this keras dot models. ये सारी layers हैं. All of these are layers. Okay. So we define a data set, load data set, which will load basically the MNIST data set, the MNIST dot load data. So it's by default built in within the keras data sets. Okay. We don't need to import it separately. So all of this is defining the train and test data, preparation of the pixels, defining the model. So this is as easy as this one. So this is define a sequential model, add the convolution layer, add the max pooling layer, add the flattening layer, then add the dense layer, and finally add the final dense layer. Flatten because this is a very highly vector, so we have to flatten it down to 1D in one dimensional. Okay. So I'll explain this on Friday in more detail, inshallah. Evaluate the model, summarize the diagnostics, summarize performance, run test hardness. So this is the hardness. So these are the train and test losses, and this is this. So this is the accuracy that we achieve on the test data, 98.392, 98.825. This is with a very, very simple neural network. And this took me some time. Maybe it took me like maybe 4 or 5 minutes, because this laptop is not GPU. So you can do this basic setup. And I've also downloaded the files for the the book that we are following right now. So in this case, they have done the epochs. So we're going to be seeing epochs ka kya matlab hai, wo kya hai. So get ready for the first assignment on Friday, inshallah ta'ala. You have to develop the test hardness. You have to develop your own backpropagation algorithm, and you have to simulate the gradient descent approach by writing your own code. I don't want you to use any function right now. You can use the functions when you go towards convolution neural networks. Okay, right now you have to understand the backpropagation. Okay, so let's meet on Friday then, inshallah. Is it okay? Okay, so please listen to the lecture. Okay, I'll just share it. Sorry?